Hi everyone, my name is Mel Morris. I'm one of the co-creators of this program called The Day in the Life of the River. Here we are on October 9th, 2020 at the beautiful Nissequogue River State Park on a just spectacular fall morning. Now this is part of a larger program that we have, which includes students and teachers going out on 11 different rivers collecting data. Given the events though of this past year with the coronavirus and the pandemic, field trips are really not allowed by most school districts, and so rather than have us lose a year's worth of data, we've assembled a panel of experts, a group of people who are willing to come out and go through our workbook, collect the data, so that put it down on video so that you then would be able to, in your classroom, go through the data, analyze it, and compare it with data from years past. So what I'd like to do at this point is introduce our experts, and then we'll get started with all of our data collection. Hi, my name is Mel Morris. I'm from Brookhaven National Laboratory, the Office of Educational Programs.
Hi, I'm Melissa Perrott from the Central Pine Barrens Commission.
Good morning, everybody. My name is Aleida Perez from Brookhaven National Lab.
Hi everyone, my name is Melissa. I'm from the Long Island Regional Environmental Education Office for New York State Parks.
Hi everyone, my name is Ashley Longo and I work for New York State Parks at the Long Island Regional Environmental Education Office.
Hi, my name is Aphrodite Montalvo. I'm with the New York State Department of Environmental Conservation in Stony Brook, Region 1, Long Island.
In following the tasks in our teacher's workbook, there are a number of different groups where we'll be collecting data. This is the first Group 1 physical data measurement that we're going to be doing. So one of the characteristics of a river is the rise and fall of the water levels. We call that the tide, and the tide is influenced by the pull of the moon on the earth, the gravitational effect. And we don't always notice the tide as it goes in and out, but we do see the effects of the tide. What we're going to do here is we're going to measure 10-minute intervals the actual rate of movement of the water to see whether, first of all, is it rising and falling, and second of all, what's the rate at which it's rising and falling. So I'm going to take a surveyor's flag like this, and I'm going to put it down at the interface where the water and the land meet. So it's just about here. Well, this is very rocky to get this in here. Let's see if we can do this. Here we go. So this will be time 0, and we'll come back in 10 minutes and put another flag in and do that over a half-hour period, and then we'll be able to figure out the rate at which the tide is moving in or out.
All right, so we're back here with the tide measurement. So as you remember, Mel put the flag in when we first got here, and then we measured it every 10 minutes for a half hour. So let's see what we found out. Is the tide falling or is it rising? So let's see. So what do we have between flag 1 and flag 2?
We have 21 centimeters.
21 centimeters, excellent. So it looks like we have a falling tide. So what do we have between flag 2 and 3?
Well, we have 75 centimeters.
Excellent, and our final 10 minutes?
Last one is 105 centimeters.
105 centimeters, so now we have our total of the tide falling, and what you can do is find out the overall vertical tide change.
Okay, so Ashley's going to be throwing an orange out into the water, and from how far it moves and the direction it moves, we'll be able to tell something about the current and the direction of the current. So, Ashley, ready? Sure.
Right.
Whoa.
Okay, so we use the compass to determine the current direction, which is north-northwest. And once we threw the orange in, we timed it for 60 seconds, stopped, measured. It went 10.8 meters. And now what we'll do is do it 2 more times, document those measurements, and give it to you to determine the rest.
All right, now we're gonna be testing air temperature, and we're gonna be doing it 3 times, once every hour. Air temperature is really important for determining what the water chemistry will be like, but also what species of animals and plants can thrive in this area depending on the season. So now we're gonna read what the temperature is right now. It is around 56 degrees Fahrenheit.
Okay, now we're going to go to the next part of Group 1, and that's going to be the cloud cover. Now again, it's a beautiful day here on the Nissequogue River, and I'm telling you, almost every year we're here, it's top 10 day, and today did not disappoint. So when you were looking up, it's clear, but then you look around and there is a few cloud around us. So I'm going to say it's clear, 0 to 25% cloud cover. Now the next we're going to do is the wind direction. And you could use two methods to determine the direction the wind is going. And remember, the wind direction is determined by the direction the wind is blowing from. It took me a while to learn that. So you could do it two ways. You can do the flag method or the water in your face method. We're going to use the flag method. And usually you have a flag around, there's a American flag far down that area, but we brought our own. So when you bring up the flag and you put it up, the wind is blowing north. So then what we're going to go to is the water. So we're looking and we're going to describe the water. Is it virtually flat, calm, rippled, or choppy? Well, today is absolutely beautiful, so we will determine that the water right now is calm. Now we measured the wind and you yelled 4, right? You said 4, so I don't need to do that. Okay, I'll do the Beaufort scale.
No.
Okay, so what we're doing is providing you with all the numbers where you and the class could do the Beaufort scale to determine the effects of the wind on the ocean water. And you'll have the chart right here that'll help you do that. Now we're going to identify the speed of the wind. And to do that, we're going to use an anemometer. This is an analog tool that will help us identify the speed. And as you can see, there are blades that the wind will whip through and then will give us a number of the miles per hour of the wind.
So I'm going to be talking about Group 2, physical characteristics of the site. And it's important to note the physical characteristics of the site because that also determines the kind of organisms that live here. And so as we look around at this site, one of the first things we notice is that it's very rocky. And there's assorted rocks here, and many of them look like they're been put here by humans. So if we look at the characteristics, just to give it some definition here, this is kind of a road ending because there is a road just up ahead of us that empties down to here. But it's also a gentle slope. Notice over to my left is the inlet for the Nissequogue River. This is an interesting place, the confluence of the Nissequogue River, the Long Island Sound flowing in and out. So there's got to be a good exchange of oxygen, salinities, and so forth. What you can see is there's a lot of macroalgae on top of these rocks. And out further, it looks to be green through the murky water, which is probably ulva, sea lettuce out here. So I would say what percentage of the bay bottom is covered in vegetation? I would say between 25 and 50%. What percentage of the river surface is covered in vegetation? There really is no surface vegetation out here. If we look to the shoreline, we see grasses that are here, but they're not on the water surface. Now what we're giving you also is the GIS coordinates of this site. The plan is, since you're not here in person, is to go into Google Maps, look up the location of the site, and then you can visually draw what the site looks like and describe some of the characteristics from what you can see looking at Google Maps.
So the experts attempted to do a sediment core with the plastic sediment tube, but the plastic wasn't able to penetrate the rocky bottom. Sometimes the equipment is not adequate for the task. We didn't have a sample from this site, but perhaps if we had a metal corer, we would have been able to. So now we're going to collect animals from the water. We're using a 20-foot long seine net, a mesh that we drag through the water. It's got floats on the top and leads on the bottom so it stays down. Our two experts will walk it out and then unroll it to its full length. The net gets pulled through the water and animals sort of get trapped between the people. When they bring it ashore, they either drag it against the shoreline or they lift it through the water. Let's see how they do. This spot is a little tough because of all the rocks, so they're very carefully picking their spot. After all the animals have been picked up and put into a container, then we can sort them by type. So we can measure the largest of each one without getting confused about our counts. So check out what we saw happening. We had a shrimp that didn't survive and a hermit crab who didn't mind an audience. All right, now we're going to measure the different species that were captured. The largest individual of each were separated. Here we are, we're taking a look at this crab. This is the Asian shore crab, an invasive, and we have a carapace width is the measurement that's preferable for most of your flat-bodied crabs. Now this is a long-clawed hermit crab. This is the common shoreline hermit crab. The measurement really isn't that important because, as you see, we're measuring the snail shell that the hermit crab borrows, not the crab itself. Next up, we have a grass shrimp, measuring from the tip of the nose or the rostrum to the tail, making sure we start at the 0 so we get an accurate measurement. This is actually a snail, not just a shell, it's alive, and that's the mud snail. Expertly scooping up this silver side, nose to the 0, gives us a measurement of just short of 5 centimeters. We should measure it to the millimeter because these animals are relatively small. And then our killifish, our measurer makes a mistake here. Look at the nose of the killifish. She pushes it to the edge of the ruler instead of the edge of the metric scale. So we're going to subtract 3 millimeters, which is that distance, and get our measurement accurate.
Now we're going to talk about the Habitat Association Survey, and it's just as important as the Aquatic Biological Survey that we just did seining. And the importance is that this is a total environmental biological inventory. So we're not just understanding the species in the water, we're also understanding the species that live in this site on land.
At this site, the habitat of the study area is the edge of the river, which is a salt marsh. While there's trees in the higher altitudes, the grasses here are salt marsh cordgrass and saltgrass, mixed in with a few other salt marsh species like glasswort. This bed is tidal and is really well adapted to the salt inundation during high tide. As you can see, it is just levels of grasses all the way around the shore on both sides of the river and on the islands inside.
So let's take a look what we've found already. It's been an incredible day for biodiversity here. So far, believe it or not, we've had a wild turkey right here. We've had raccoon. Both we saw the tracks. We have a variety of gulls. We definitely have a laughing gull because we've heard them all day.
We have cormorants that you've seen in this photograph. We've seen great blue heron, egrets, squirrels, 2 red-tailed hawks, the osprey that's still here, and also a variety of oysters and clams and mussels, a plethora, so many of them. So you can tell already that this site is just rich with biodiversity and a very healthy ecosystem.
Hello everybody, so we are now in group 4. It's the chemical testing, which gives us an indication of the quality of the water that of the Nissequogue River today. So one of the first things that we did was collected the temperature for the water sample. We use a thermometer right here, and we did that in centigrades. So when you see your data information, you will find that we've had about 17.5 degrees centigrade in the different sites that we collected the data from. Okay. Now, the first test that we did was the dissolved oxygen, just the levels of oxygen that we will find in the water, in the waterways. We collected 3 different samples, and one thing that we noticed was that the amount of oxygen was actually different in all the 3 different samples that we surveyed, which is something for you to think about what that might mean. These chemical tests are a color changing test, so every time you see us changing color, it tells you that something happened. And we have this color-coded key that when you put your tube against it, it gives you a sense of the numbers, how much of dissolved oxygen in this case the water has. So I'm going to pick this sample right here, and we're going to put against the white, against our color-coded card, and we see this about 2.5 parts per million of dissolved oxygen, right? The next chemical test that we did was the pH of the water, and we did already 2 samples here. Okay, this is an example of what the test looked like, and I am going to have Aphrodite is going to show us the 3rd sample or the 3rd testing for the pH.
So basically, I'm just going to take this pipette. I'm going to take some of the water that we just took from the Nissequogue River a little bit earlier and add 10 milliliters to this tube. I'm going to make sure, as I'm adding the water, that the meniscus hits the bottom of the 10 milliliters. We always measure the meniscus, that bottom of that little tube, and that's the proper measurement. We don't measure from the top. So let's get this top. Remember that the pH is measuring the acidity, or how basic the water is, or how neutral it is. So we're almost there. Okay, we have 10 milliliters in. So how we're going to do this is we're going to pop in one of these pH tablets, and it should basically instantaneously tell us the pH of the water. As you see, she's not touching the tablet because we don't want any of the acids on our skin to affect our sample. So we're going to go back and forth a few times. Let this tablet dissolve.
And you notice that we're doing by immersion, so we don't want to shake our samples. Okay, we don't want to introduce.
Okay.
All right.
So now let's compare it. It looks pretty yellow. It looks like it's pretty neutral right here. So between 6 and 7, you say, or 7?
Between 6 and 7, so we're going to call it 6.5. Okay. All right, the next test that we did was our phosphate, okay, testing, how much phosphate we have in our Nissequogue River. Again, it's a change of color. We put 10 milliliters of water in a tablet of the phosphate indicator, and when we press it against the the colorimetric shard, we found it to be not quite 4, but around 2 parts per million or so. Next test that we did was the nitrate testing. Tells us how much nitrogen we can find in our waters. And if you noticed, this test has a very peculiar, it's a little different than the other ones because we put the tube inside of a little bag. And the reason we do that is because the test itself is sensitive to light, UV light. So in order to get a reliable testing, we're covering it in the bag so the light does not destroy the chemicals. We're going to take it out. Okay. We'll give it a little bit of a mix. Again, we have is a color change. We put it, get our color chart. And this test was a little interesting. We're going to call this at least 5. And the reason for that is because even though it might be a little lighter than 5, our scale only goes 5 and above. Okay, so we can't say anything below that. So we have completed all our chemical testing. If you notice, we have tested every single chemical in triplicate. So we did that 3 times. Okay? The more times that we do on any of these tests, the more accurate our result we expect it to be. Now it is your job or your challenge at school to calculate the average of these reading samples for your data assessment.
And last but certainly not least, what are we going to do with all these samples after we have completed our tests? We can't put them back into the water. That's basically polluting the water. So we have our container that we put all of our wastewater in, and this will be properly disposed of in an appropriate area so that we do not actually pollute or harm any of the habitat in the river that we're working with.
Okay, now part of group 4, Aleda and Aphrodite are about to measure the salinity with a refractometer. The refractometer is an excellent tool to use to determine salinity of the water. You have to make sure it's calibrated to a 0 level. And to do that, you're going to place distilled water on the glass surface, and you're going to look through the eyepiece and make sure it's at 0. If it's not at 0, the refractometer does come with a screwdriver, so you're able to calibrate it to that 0 level. So once you're at 0, you're going to wipe off that surface and make sure you're back to a clean glass surface, and then you're ready to measure your water samples, salinity levels. So you're going to do the same thing. You're going to use a pipette, and you will add a sample of your water, close it down, and then you can look through the eyepiece again to determine your salinity levels. Now, Aleda and Aphrodite did this 3 times at 3 different locations, and we're going to provide you those 3 numbers, and you can come up with the average of salinity at that site at the Nissequogue River.
All right, so now we're going to be measuring turbidity using a Secchi disc tube. Turbidity is the amount of suspended particles that are in the water, and it contributes to our visibility and how far we can see in the water. So what we're at right now is 1.2 meters, and what's going to happen is Melissa's going to release some water from the tube, and I'm going to be looking down to see when I can see the Secchi disc that's at the bottom of the tube. So we're ready. All right, I can see it. And we are now at 1.09 meters. So based on where we started and where we ended, we can conclude that the water visibility is very clear here.
Well, thank you for joining us today here at the Nissequogue River. What a beautiful day. We would have rather have had you all with us, but thank you for letting us step into your shoes for the day to experience this beautiful ecosystem. And fingers crossed, we'll be back together again next year to do this together. See you soon.